Next topic, phase portraits. So again, in this class today, we're reviewing how we might evaluate the equations of motion. I mentioned in general 3, could be more, those 3 come to my mind: closed form solutions, numerical solutions, and phase portraits. You know, I should take a second and just say, what do I mean by a closed form solution? I suppose I mean exact. You might say exact solution. You also might say a closed form solution means there's a finite number of steps, a known number of steps to get to the solution. A numerical solution is one that's iterative. It assumes, you know, it makes some assumptions on the systems and solves a similar problem iteratively, a very simplified problem iteratively in small time steps, trying to replicate the behavior of the system. There's a third method that's really interesting, and it's called phase portraits. I frankly am only exposed to phase portraits through dynamics. So I think of it as a dynamic tool, but frankly, I think it really arrived from people I think its origins are probably in mathematics, although mathematics and dynamics go close hand in hand. I think of phase portraits as a dynamic problem. Again, you'll also find this in differential equations approaches, but we're going to talk about phase portraits from a dynamics case. And it gives us an alternative way of evaluating or solving equations of motion. So let's consider first, let's consider the problem we had above. Let's consider a case where I just have a mass spring. I'm doing this as a little introduction. So I don't have a damper. My equations of motion are x double dot plus kx equals 0. It's unforced free response vibration. When I solve this, I get 2 roots, but they're imaginary, plus or minus the square root of this thing. So my solution becomes, you know, just from above, x equals some amplitude a times the cosine of omega t plus phi. My real part is 0. You know, we can see that my r would be the square root of negative k, and I'd get plus or minus that. So there's no real part here. So that's my solution. My x is a cosine omega t plus phi. My x dot is negative a times omega sine of omega t plus phi. And if I now, so I've got the solution, so there's no reason, this is not phase portraits, right? This is what we just did, not phase portraits. This is what we just did. And if I plot, I can see that my x, I have some phase shift, some phi, so let's assume this is my phi here. So when t is 0, if I did that right, maybe that's negative phi, maybe my sign is off. We'll just assume I have some phi. I guess that is a negative phi value where I plug it in, and that's what my response looks like at the 0 point. And so then I just get this response that looks like this. This is my A amplitude. Of course, this is my omega. Now here's my t. And then at my x dot at that same, over that same scale, when t equals phi, I'm going to get 0, go down negative, come back to 0, positive, come back to 0. So no, I'm out of phase by 180 degrees. Let's see these things. And so on. So there's my response. Now, if I were to, okay, so I can see that, and this is my time response to the system. So I've got 3 parameters here, right? I've got time, I've got x, and I've got 3, x dot. So I got 3 equations, all parameterized here in t. So I get 3 terms, t, x, and x dot. I get the 2 equations. However, if I wanted to get rid of my parameterization t, so I'm going to eliminate t from these equations. And I can do that here by square and add both equations. By the way, anytime I have a term that's tucked into a sine or a cosine, a sine and a cosine, my Pythagorean identity often will get rid of it. So if I square and add both, I'm going to get a cos squared. I'm going to get a minus a omega squared sine squared. If I move the a over, if I divide that by omega, both sides by omega, notice I get a cos squared, a sine squared. So I'll get x squared plus x dot over omega squared equals a squared. Because I got a cos squared, a sine squared plus cosine squared goes to 1. And if I see that guy, know that this, now I've just got 2 terms, x and x dot. Here I had 3, so I had 2 equations, 3 terms. I eliminated the t in the process. I might say, why eliminate the t? Well, frankly, the t, well, t is time. If I want to know time, that's fine, but time, t is what made this thing differential to begin with. I had to solve it, and I had to solve in terms of time. If I get rid of t, now I can look at a different space. Now I can look at an x and an x dot space, and I've got a fundamental relationship between those. If you think of our conic section, just as a quick aside, I get some ax squared plus some some bxy, I think of bxy, plus cy squared plus dx plus ey equals f, something like that. And then AC, if AC is, this is all from my textbook, if AC is greater than 0 and C is not A, then that means my section is an ellipse. And here my A would be 1, my C would be 1 over omega squared, and they're not equal to each other. So I could I can rewrite this in some form, and I get, well, let me rewrite it. Well, yeah, let's do that. Here I've written it as a conic section. I can see that I have an ellipse, so I can write it generally as an ellipse here as x minus h quantity squared over a squared plus y minus k quantity squared over b squared, where the center is at hk, and the dimensions of the, and that thing equals 1, or actually it would equal, 1 in this case. A squared and b squared give me the dimensions of my ellipse. If it were a circle, A would equal B, and I could move them over. A would equal B, and they would be the radius. Ellipse, I need to leave my A and B out here. I get a, I got a chat. Let me check on this. All right. Preston is solving his own problems as I ignore them. Preston, you're encouraging me to ignore you. Don't do that. Well, actually, it's great that you're solving your own problem. Don't let me just ignore you, though. So I'm trying to watch that. Why did that go away? I thought I had that. Stay up. Huh. Oh, well. All right, so anyhow, I can see that I get an ellipse, and, here's my ellipse. Oops, let me move it over here. So I get this ellipse. I have x versus x dot. This is my A, This is my B. And in this problem, my A was equal to, well, cap A, and my B is equal to A times omega. And this is the solution. This is the solution to my dynamics right here. This is a solution to my dynamics. It tells me how my response goes in terms of my two variables, x versus x dot. The only thing that's missing is I don't have time. I don't have time, but I can see this motion. All right, so this is a solution. It's an alternative. Let me just say it's an alternative solution to my dynamics. And I can say, you know, I can extract dynamic information. I can do various things from that. Now, this is similar information. In this case, I have no t, so I just have x and x dot. So I just one graph will do it. Above, I have t, so I have three parameters. So I can look at x versus time, x dot versus time. You know, at every point along here, they should all be matched. So for example, here x is some positive value, its maximum value, x dot is 0, so that would be here. So let's call this cap A circle. Then my x went to 0, my x dot went negative, so that would be here, down here. Then my x dot went max negative, my x went negative, my x dot is 0, so that's here. Then I move back up here to my x being 0, my x dot being positive, and so on. And then I repeat. Okay, so you notice this, I start back at A, so I'm moving around. So as time goes forward, I'm just marching my way around. I can see the cyclical nature. I see my cyclical nature here. It's continuously closed. You can imagine if I had some decay in these problems, I had some decay, maybe the response started to look like this, right? What would you expect to happen down here? Well, I'd kind of expect it to start spiraling inward, right? And frankly, I could see that quite easily here. If I had growth, you know, I would expect it to grow up here in time, and I would also expect it to grow in my phase space. This is my phase space, by the way. Or my phase domain. This is time space or time domain. And they give me similar, really the same information. Okay, so phase portraits gives me an alternative way to look at it. Are you impressed? Preston. I'm going to look at the check. Preston, are you impressed? Can't even keep my chat up. How is Preston going to be impressed? Yeah, all right. Okay, everyone's impressed. All right. But wait, there's more. There is more. Okay, I feel like the guy on TV. You're impressed with this, but you haven't seen anything yet. For $19.99 and 3 easy payments, I'm going to show you why phase portraits are cool. That phase portraits do something else. And that is, can I get to here without solving the differential equation? Can I go straight from my equation of motion to my phase portrait? Well, I've kind of played it up, and the answer is yes. And furthermore, what if I get an equation of motion that I couldn't get a differential equation for? You know, it's nonlinear, it has other things. Can I go still from the equation of motion to the phase portrait, even if I couldn't do the differential equation? Again, the answer is yes. Okay. Frankly, I think you can go in all cases. However, my calculus breaks down pretty quickly, so you do have to do one step in calculus, but it's not that bad. Okay. So this is what makes them so exciting. I can go from the equation of motion straight to the phase portrait, plot this thing, and never have to solve the differential equation. Let me show you how. I start with my equation of motion, mx, and I'm just using the simple one. Mx double dot plus kx equals 0. I'm going to take what's called the first, I'm going to take the first integral of motion. All right. Now, recall in time domain, I'd have to integrate with respect to time, right? But I'm ignoring time. So I'm going to integrate with respect to, that's what I did in time. In my phase space, I'm going to integrate with respect to space, which is x. And that's the beauty. I don't know who came up with this, but it's really quite amazing. So I'm going to integrate this whole thing, this whole equation of motion with respect to dx. Not dm, dx. So I get the integral of mx double dot dx plus the integral of kx dx equals the integral of 0 dx. All right. So I have to do that. The integral, let's start with this guy. That one's the easy one. So the integral of kx dx, well, that's going to be 1/2 kx squared. Okay, that's easy. Integral of 0 dx, well, that's just a constant, right? So, you know, the integral, recall, is the integral, it's the inverse of the differential. So if I took the differential of a constant, I get 0. Integral of 0 is a constant. And I'm going to call it E, which foreshadows, look, does this look like something to you? Yeah, it looks like kinetic energy. So these terms are all going to be energy. Man, we keep coming back to energy. So I'm just going to leave this as an energy, and it's a constant. I can see this is going to be energy, or at least energy-like. I'm missing my mass here, so we'll call it energy-like. And then finally, I've got to get the integral of mx double dot dx. Now, m is not a function of x, so I just get the integral of x double dot dx, and we'll do a couple steps here. This is a little bit of trickery that we do. Once you see it, it's the same thing all the time. I'm going to rewrite my x double dot as my derivative of x with respect to time. That's fine. And then I do the little game where I multiply by 1, which is dt dt, and then I've got a dx. So we can cancel those two dt. Yeah, we can cancel those two dt's. This seems kind of odd, but I'm going to then move, I'm going to rewrite this as the dx dot dx dt, right? And dx dt is just x dot, so I'll put it first. You know, I'm going to flip it around. So I get x dot dx dot, and that is simply 1/2 x dot squared, you know, plus a constant, and I got to bring my m's down, m. Oh, by the way, I said that's energy like, that is energy. I don't know what I'm thinking. I'll leave it energy like. I guess energy is like energy, isn't it? But we need the m here, so I got confused. That's fine. So we get these terms. So we get 1/2 mx dot squared plus 1/2 kx squared equals E. I took the first integral, I get this thing, okay? This is the first integral of motion. And by the way, this is exactly, I mean, it's just one equation in terms of x dot, and from here, I can plot directly my x versus x dot. And furthermore, I can see it's of this form. Look, it's of this form, okay? So it's x, I got an x squared, a y squared, or an x squared and x dot squared divided by a squared divided by b squared equals 1. So I can rewrite that. Yeah, so I get like x dot squared. Let's see, I have to divide that by something. I guess I'm going to divide everything by E. So this thing is going to be E over, I guess it's going to be 2E over M, and this is going to be x squared 2E over K, and that equals 1. So this problem here, see, I've gone back and reproduced my ellipse where my major axis A is this 2e over k, and this minor axis is 2e over m, and this is my x, and this is my x dot. All right, there you have it. So now I can solve my differential, excuse me, yeah, I can solve my equations of motion, my differential equations, without taking a differential equations class. Well, I just have to take calculus. I take, instead of looking into time, I look at it in space. I take the first integral of motion, okay? And I'm always gonna have an x double dot term, and that term is always, I'm always gonna do this little trick. So my x double dot term will always give me a 1/2 mx dot squared, always. I'm gonna have some other terms in terms of my variables, my generalized coordinates. So I'll just take the derivative with respect to those. That's straightforward. And then I'll always get energy on the right-hand side. So, so this gives me a straightforward way to solve these things. Why did we even spend time solving differential equations, I wonder? Recall though, you can only do this for one DOF at a time at least, okay? So that is kind of the biggest limitation to me, but there you go. Now, but wait, that's not all, right? I know you're expecting a lot, but do you expect more? Well, you should, because there's more, all right? So we take the first integral, and then we plot, and here I've said, well, we have to recognize the form of an ellipse. Do you think they're always going to be ellipse? No, not at all. Only very special cases, no decay, no growth, no decay, and a constant oscillation. So frankly, this is probably the least common case. So we can always go straight from the first integral. So let's back up. So we go straight from the equation of motion to first integral to the plot, and I don't have to derive the form. I just go straight to the plot. So I'm just going to plot it. In other words, stick in a value for x, solve for the value of x dot, plot it. Stick in a new value of x, put in, solve for a new value of x dot, plot it, and so on. So frankly, that process is fine. And you might say, well, that's numerical, but really it's just plotting, okay? This is the solution. The solution's right here. Then I just have to plot. Now I'm going to show you kind of a handy way to plot without having to necessarily go to MATLAB, although you could do that, although you can always do that. And the third way goes like this, all right? So let's look at plotting this thing. So I've got my 1/2 mx dot squared plus my 1/2 kx squared equals e. Okay, that's my term. And this is the amazing thing in the first integral motion. This shows us just the relationship between these energy methods and these vector methods. We derive this thing using vector, but we took the first integral and then we get back to an energy method. It's really kind of an interesting, you can see how everything's related here. All right, here's how I'm going to plot. I'm going to recognize that I've got a couple terms. I've got this constant term. I've got, I'm always going to have some dynamic term. So this is my kinetic energy. I might have set up above, I saw the K and maybe said kinetic energy, but that's not the case. The kinetic energy is the one associated with motion. And then the other terms are going to be other energy terms. And depending on the nature, I mean, they could be decaying or non-decaying. But in this case, this one's going to be a potential term, a potential energy. We're going to call our kinetic energy T and our potential energy U for the remainder of this class. I know there's some different terms that are used, but we'll do that. So what we're going to do first is we're going to, well, the idea is we're going to say that, look, T is equal to E minus U. That's the basic idea. And then T is always the form x dot squared. So we're going to go one step farther, and we're going to say that it's the x dot is always the square root of E minus U, okay? And there are some other terms, times some constant out front, which will kind of drop, okay? So this is going to give us an easy way to plot. So what do I have to do? Well, I have to put in my constant E, assume some energy state, subtract out the current U, and that gives me the x dot. So let's look at this one as an example. So first I'm going to do my U E plot, and I'll consider some various values of energy because there could be many. Oh, I lose a dot. Got another one. Okay, looks like I've got the. You're thinking this one. I think I've got it here. All right, I can choose different values of energy. So I'm going to choose. There's an E1. I'll figure out how to keep this darn thing pinned up here. Yeah, I'll come back and do it later. Yeah. Here's an E2. I mean, I can go on and do this forever, as you can imagine. Here's an E3. Maybe I'll stop there. Okay, so there's 3 E's. And then let's look at our U. So our U is 1/2 kx squared. And so, you know, 1/2 kx squared, that's always going to be positive, correct? And so it's a parabola pointing up. So I'll get just something like that, you know, as x increases. So this is my 1/2 kx squared, you know, for some value of k. It's always going to take that shape. And then I'm going to see that my x dot, now right below that, that's my UE plot versus x. And this is now my x dot versus x plot. And I know that x is E minus U, the square root of that, okay? And my x dot always has to be real, so I can only exist where E is greater than U. So let's start with my E1 case. I'll go to the red for that. So for the E1 case, let's start right here in the middle where x is 0. So here, this is E minus U, right? So the square root of that is going to be my x. So it looks like it's some large value. So there's x, and it's plus or minus that, by the way. So there's my 2 x dots. Then as I move my way over, I can see I have some lesser values. I move to the right, out to the point that I go to 0. So I get lesser values, working my way out, okay, like so. And as I go to the right, I can see the same thing. Lesser values moving out to here. So that gives me my, oops, let me do that. Plot, I don't know, ellipse there. Next, I go to my E2 term, my E2 energy. So if I start with a lesser energy, I can see, we'll start right in the middle when x is 0. I get this guy for some maximum x dot term plus and minus, and it decreases down to 0 here, like so. And then finally, I can see the same thing for my E3 energy. It's going to be 0 there. Boy, my plot's not very good. I hope you're making out, though, my idea. Okay. Now, let's look and see what happens. What happens if I'm out here? Well, if I'm out here, my U is greater than E. So E minus U is a negative. I get the square root of a negative. That gives me an imaginary number. X dot cannot be negative. I can't, excuse me, imaginary. I can't have a non-real X dot. Now in the solution before, I can have a non-real solution to X when I assume that other form. But at this point, X dot must be real, okay? Because it's a scalar thing. All right, So these are my motions, all right? And then the last thing I need to do is get the directions. Okay, so let's go back. And this is my motion. So for my E1 energy, that's how the thing behaves. So if I give it initial energy, it just constantly moves on the circle. And the question is, which way does it go? Well, here's how I look at it. If here's what I do. For a pod, I start by thinking in terms of x dot. If my velocity is positive, which I am in this upper curve, then my x always must be increasing. So here I've got a positive velocity, so I have to have increasing x. Down here, I have a negative velocity, so I always have to have a decreasing x. That's how I get the direction. And you can do that on all of these. Wherever there's a positive velocity, you can have an increasing x, negative velocity, and a decreasing x. So that's how this thing moves around. Okay, so let's now pick an example that will show how this stuff works out. If I jump quickly over to the to our website, I just want to mention to you that I've got several examples. Got your puck in a spinning slot, got your thumb in your spring. Oh, and I've got an amusement park ride. Oh, we should do that for one of the dollywood rides. Any 1 degree of freedom ride is nice. Actually, these things are really nice. If we could have an example of that. That would be a lot of fun to do. We'll come back and talk about that next week. But at the moment, let me, well, let's look at one that's not here. We're going to look at a simple one that's not here very quickly, all right? I want to give one example that's not listed on these. You can go look at these. All right. So let's consider, and I know this is a pretty trivial example, but it allows us to do it quickly and see the method. So let's look at this pendulum. Okay. Any of the problems that we've been solving together can be treated here, frankly, any of them. I'm going to start with I'm going to pull a simple one here so that we can move through it quickly and get the basic idea. So I'm just going to have a single pendulum, and let's look at how this thing behaves. Now, so pendulum, it's moving with some theta dot, and I want to know the behavior. So we'll start with our typical thing. I'm going to create some initial frame, an N1, N2. I'll have a frame attached to the body. Call my body fixed frame B1, B2. I only have 1 degree of freedom, so I only need to add 1 extra frame. I'll start with my kinematics. My kinematics will be a relationship, a few things, a relationship between the B frame to the N frame. Looks like it's a rotation around the 3 by theta. I can look at the rotation, the angular velocity of B with respect to N. Looks like it's theta dot around the B3, which is theta dot around the B1. My location of my center of mass out here, we'll call that G. I give it some vector R from O to G. That's just going to be the length of the pendulum in the B1 direction. The velocity will be the derivative of that first in the B frame plus the angular velocity B with respect to N crossed with the R. This is my omega cross R term here. I get a 3 cross a 1, that's a positive 2. So I get L theta dot in the B2 direction. My acceleration of the puck, I now need to take the derivative first in the B frame. So it's going to give me L theta double dot in the B2 plus the angular velocity B to N crossed with this term. I'll write that one out. It's 0, 0 theta dot crossed with 0 L theta dot 0. These are both in the B frame. It gives me a 3 cross a 2 is -1, so let's write those out. So I'll write out the whole term. So 3 cross a 2 is -1, so it's a negative L theta dot squared. That's the only term I get from the cross product. I add in this term L theta double dot and 0. There's my kinematics. Now I go to my dynamics. This is simply a particle. So I will only have Newton's part of the equations. For my free body diagram, I've got the puck, or the little mass. I've got some tension. I've got mass times gravity. Need to project mass times gravity. I'm going to write the equations in the B frame. So I need to take mass times gravity, which is in the negative Y frame, pre-multiply by the projection from the B to the N transpose. So I'll write down here cos theta minus sine theta 0, sine theta, cos theta 0, 0, 0, 1. Give me negative mg sine theta, negative mg cos theta 0. Okay, that's my gravity vector in the B frame. I can write my dynamics. So my sum of forces in the B1 direction can give me a negative T1 minus mgs theta. Oh, you know what, everyone? I messed up. Everyone catch me in the chat. Well, it's one thing about going so fast. Yeah, okay, Drew caught me. Okay, Drew caught me. I made a mistake. It looks like my mg is in the N1. Drew makes it look so obvious now. And it's in the positive N1 direction. So I need to multiply by the first column, and I get a positive, so I get mg cos theta minus mg sine theta and 0. Now you might say, well, I really would have preferred just to have said cos theta times mg minus sine theta. And that's fine. That would have been easier in this case. But the minute you get more than one rotation, it just gets almost impossible to see intuitively. So, but the method here doesn't change. So I'm trying to practice the method. Back to our dynamics. So I get T1 plus mg in the cos theta, mg cos theta equals negative L theta dot squared. Second equation, minus mg sine theta equals, should be an m here, m L theta double dot, and 0 equals 0. My three equations, I get two unknowns, T1 and theta double dot. I picked this problem because they're explicit, although if they weren't, that would be fine. I'll show you later on how we could solve for those. But at the moment, they're explicit in the unknown. So this is the guy I'm going to pull out as my equation of motion. So I get ml theta double dot equals, or minus mg sine theta equals 0, or I could rewrite this as theta double dot minus g over L s theta equals 0. Now, this is the pendulum equation, which we know and love. What do we always do? Well, we always say small angles, and we make the small angle assumption, so we get theta double dot minus g over L theta equals 0. That's now a linear differential equation. We can solve it. We frankly just solved it, and we get that particular motion. Okay, we get the motion that we saw above, that constant oscillation motion. So it just sits there and swings forever. However, I don't want to do that. I want to know, what about large angles? I'm interested in what happened. I'm thinking about the dollywood ride where I'm swinging way high in the air. The thing is, you know, no one's going to pay, what does it cost to go to Dollywood for a day? Kevin, how much does it cost? How much does Dollywood for a day with your family set you back? $300, $200? Okay, no one's going to pay $200 to take their family to Dollywood to get on a little dizzy car or whatever and swing at 10 degrees, right? You're paying for 20 degrees. You're paying for 40 degrees, right? You want to feel the, you know, the ketchup that's stuck on your cheek go flying off, okay? That's what you're paying for. So how do we evaluate that? Well, we can use our phase portrait. So let's jump to phase portrait method. What's our method? 1, get the equation of motion. Got it. Theta double dot minus G over L sine theta equals 0. Step 2, take the first integral. And you know what? I'm going to pause for a second and let everyone catch up. When I get excited, I go too quickly. Okay. Can you read? State the first line after dynamics, yes. Okay, so Kevin just asked me to restate the first line after dynamics. So here I was just saying, we're just going to write Newton's equations. Since we just have a particle, in this case, our rigid body is a point mass for this simple problem. So the first one is sum of forces in the B1. Second one is sum of forces in the B2. And then this one is sum of forces in the B3. Okay. So we're interested in the behavior for large angles. That's what we're curious about. So we're going to evaluate our equations of motion using phase portraits. We're going to break it down to these steps. First, get the equations of motion. We did that. Second step, take the first integral. We're going to take the first integral of motion. In this case, our motion is theta. So we're going to take do we take a dx or do we take a d something else like a d theta? Well, clearly we want to take the derivative with respect to the parameter that we're investigating. In this case, it's theta. So we'll take the integral of this equation of motion, put in right here, d theta, and that will give us these terms. We're going to get the integral of theta double dot d theta. We're going to get the integral of minus g over L sine theta d theta, and we get the integral of 0 d theta. Start on the right. The 0 d theta will just give us an E, a constant. And again, this is the one that's like energy. I dropped mass, so it's energy like, okay. This term, we get the derivative of sine theta, so that's negative cos theta, right? So it's going to be positive g over L cos theta, because the derivative of cos theta is negative sine theta, yes. And then finally, we get the derivative of this theta double dot, but recall we can rewrite this as the, excuse me, I'm saying derivative, I mean integral. The third term is we get the integral of theta double dot, which we can rewrite as the integral of theta dot, which gives us 1/2 theta dot squared. So this is our first integral. And it's actually, I'm saying first integral of motion. Need to be careful. So this is the first integral of motion. Three, we're going to plot. So to do that, we'll first plot E and U versus X, and then we'll plot, second, we'll plot X dot versus X. So first I'll get my E and U versus X. And I'm going to consider a couple energy states. I consider a high one, call it E1. I'll take an E2. And an E3. Okay, now we need to plot the U. In this case, the U is, well, I say the U, but it's the non-kinetic term. So this is G over L cos theta. So what's that going to look like? Well, constant times cos theta, or not X, my bad. Theta. So I need to plot some constant times the cosine of theta, and so that's just going to be, say it's going to be something like this. Up, down, up, down. Okay. So there's my G over L cos theta. And I probably should have plotted that first and put energy levels around it. Let me, for fun, add another energy level way out here. Let's add an E4 way out here. Okay. So now I'm ready to plot my, oops, I got the wrong one. Darn it. Pen. I guess I had the right one. X, theta versus theta dot. And let's start with the E4 motion, okay? So if I look at the E4 case, I can see that I'm, I can only consider, here's the thing, I can only consider motion where my potential term, or whatever you call this energy term, is greater than the input energy, right? So these are the only valid regions that I have. And frankly, when it goes on out, it would be one over here, right? So I can go on out as far as I want. So I get valid areas there. And it looks like I get an ellipse, or actually a sinusoid, right? The difference between, I just get these sinusoidal motions between. I'll just draw them like these things, okay? So this is the motion I have at E4 energy. And I get little ones all out here. And by the way, when my velocity is positive, I'm increasing, so I'm always traveling this way. My velocity is negative, I'm traveling this way. So I could exist in any one of these states just going around and around and around. Now, let's move up to E3 energy. What about E3 energy? Looks like it's the same thing, right? I can exist only in this region up here. I come to zeros right here, so I get the same kind of motion, just larger. So this is my E3, and again, where where I've got a positive velocity, I'm increasing, positive x, increasing x, negative velocity, decreasing x. Okay, I'll work my way up to E2. Look, E2 is right at these peaks, okay? So I exist really everywhere on this curve, but I come to 0 velocities here. So here, I'm coming down to 0 velocities. So this is my E2 case. Like this. Oops. And then finally, if I go to my E1 case, you know, I have motion that exists everywhere. Looks like I'm a minimum at these points, plus and minus. And so my graph got a little carried away. The minimum at these points, and then increase in between them. So I'm like this. Okay. So this is my E1 energy state. And a positive velocity means I'm increasing in x. A negative velocity means I'm decreasing in x. And these are my 4 motions. Now, what do they mean physically? I'm going to pull me up. Oops, I'll do that. Okay. So I'm going to go over here. Nope. Nope. Yes. Okay. So what do these mean for the ride? Well, again, Kevin is an engineer. Oh, you guys are all engineers. So Kevin knows how to go to Dollywood with his family, you know, inexpensively. But you look at the rest of the people, they're paying a lot of money. So how does Dollywood make rides where people are willing to drop $200 to $400 a day to take your family for Dollywood? They do that with large motion on one of their, like the timber tower ride, right? So it's moving back and forth. So let's look at the motion. So here's the ride. So, and notice these are all driven by initial conditions. So we're assuming the ride is one where you give an initial condition, it starts the motion. So for a small input energy, initial state, you've got some small motion here, that's E1. You've got some small motion, and in this example, the small motion exists here. Let's see, that's theta equals 0, so I'm over here at 90. It looks like I'm over here at 180 in my case. Hopefully that matches up to my picture. Well, oh, Drew. I'm going to blame Drew on this. Drew, you usually catch me. I missed a sign. See that sign here? Did I miss it? Yeah, I missed my sign. Okay. Okay, everyone. I missed my sign. I missed a sign. I should have had a negative in there. Okay. I've got a sign problem, okay? If I flip the sign, that would have flipped my pendulum, and I would have then been at 0 rather than 180. I would have shifted by 180. Okay, little mistake there. Should be shifted by 180. If we could just assume that my N1 is up, and then I just crank my way all the way around, then that would make more sense, right? That's what I basically did. So I made a little mistake, but that's not going to deter me. Let's go back. All right, so we're off by 180 because of my sign error. But right here, this motion is a small amount of energy given, and it's oscillating just back and forth at a small motion. And I'm just going around, you know, positive velocity increasing theta, and the negative velocity decreasing theta. So I'm just doing this. I'm going around and around and around forever. It never stops. Okay? It never stops. Now I give it more energy, right? So I'm going to go to an E3 state, and I got more energy, so I get a larger displacement. So now I'm doing this, okay? And you can imagine if I increase the energy, but I'm just going back and forth. So I come out to this point, 0 velocity, non-zero displacement, and then I start with a negative velocity, decreasing displacement to negative. I just go back and forth on that. And as I increase, I get larger and larger. Now, what happens to the E2 motion? Look, the E2 motion is very interesting. I mean, this is beyond extreme. I'm actually doing this. So I start out at some maximum. I guess, again, I'm off by 180. I should be shifted. But here we'll say at 0. So I start here, let's say here, and I go in a positive direction all the way around to here, and I come to a stop, right? And then, so just before that, I would start here, go all the way around to here, all the way around to there, back and forth. Well, once I get to this point, I start here, I go all the way around, I come back to that point, you know, I go all the way around back there. Now look what I could do. I could just reverse, so just went here, all the way around to here. Now I could reverse and then go back, or I could keep going, go on the same way, right? So I could go from here to here to here if I wanted, which would be around, around, and around, and around in the same way, or I could go, you know, around and then back like that. I could do either one. And Dollywood, I guess, does that, right? They take the ride, they run you to the top, they bring you to a stop. Now they put some energy into control it, and then they run you back the other way. Or I could even give it more energy. I could give it E1 energy, and in this case, you know, once I get going, I just keep going. I don't even come to a stop. I just keep going around and around, and that's what I'm seeing here. It's all a function of the energy that goes into the system. Let me note one other thing. These are dynamically stable. These are instantaneously stable conditions, right? They come to here, and the thing comes to rest. And then, well, let's look at that. Let's look at this one. It comes to rest, and it has 0 displacement. Well, in this case, it has 0 displacement. And actually, any of these are fine. It has a 0 displacement and has 0 velocity. That's what I'm trying to say. And so it can, and at this point, I could either go off this way or it could go off this way, right? This guy comes to 0 velocity and he has to continue on. So these phase portraits show me the variety of motion in the various cases that I have. In this problem, it's oscillatory. My angle can grow, or it can be it can stay constrained within a motion. It just depends on the energy that's given. Okay. Well, that's going to conclude everything I want to talk about today. Let's take a minute or two. Stop